Welcome to the Explainer. It's actually kind of wild to think about. You can pull out your phone right now and instantly stream a 4K movie without a second thought. But trying to render a truly realistic, physically accurate virtual world for thousands of people at the exact same time, that remains incredibly difficult. Today, we're diving into a fascinating puzzle in the world of computer graphics and exploring how some cutting-edge research is proposing a pretty brilliant way to finally solve it. Over the last decade or so, we've seen movies, music, basically our entire digital lives move seamlessly to the cloud. So it's a super valid question to ask, why haven't interactive graphical applications like those massive multiplayer video games fully made that same leap? I mean, cloud gaming services definitely exist, but they haven't exactly wiped out home consoles or high-end desktop PCs yet. Think about it. If a massive data center can stream a high-def movie to millions of viewers at once, what's stopping them from doing the exact same thing with a massive interactive 3D world? Well, it all boils down to one massive computing bottleneck. Basically, to make a modern game look hyper-real, the underlying math requires a completely separate, incredibly powerful processor for every single user. The servers literally have to calculate millions of individual light beams for each specific player's camera angle. And because our current lighting algorithms render those viewpoints entirely independently, they just don't scale. They are fundamentally not built for massive multi-user applications. So here's how we're going to break down this puzzle today, looking at a really brilliant master's thesis by researcher Gente van der Sanden on something called centralized irradiance caching. First, we'll hit the cloud gaming bottleneck, then the math of light. After that, we'll tackle the multi-user problem, introduce the shared lighting solution, look at fixing the memory wall, and finally, wrap up with the future of rendering. All right, section 1, the cloud gaming bottleneck. Let's look at what's actually holding our servers back when they try to render these highly immersive games in real time. If you've played a modern photorealistic game, you've probably benefited from an algorithm called Monte Carlo path tracing. Now, it sounds super complex, but it's essentially just a mathematical way to estimate how physical light behaves in the real world. It does this by tracing millions of random rays. Just imagine shooting millions of tiny, invisible laser beams out from your character's camera straight into the digital scene. Every time one of those rays hits a surface, it recursively bounces, changing trajectory based on whatever material it hit, until it eventually finds a light source, like the sun or a lamp. The result? Absolutely stunning realism. Perfect shadows, flawless reflections. But for a centralized server to calculate all of that at scale, total nightmare. Moving on to section 2. The math of light. To understand how we can actually fix this massive processing drain, we need to take a quick detour into how light behaves when it hits different materials in a 3D environment. Check out the stark contrast between these two materials on this 3D dragon model. On the left, you've got a diffuse object. Think of everyday stuff like chalk, rough plastic, or matte paint. It scatters incoming light uniformly in all directions. But on the right, you have a perfectly specular object. This acts exactly like a pristine mirror or clear glass, reflecting or refracting light sharply in one very specific direction. This distinction right here is absolutely vital for the optimization we're about to explore. Here's the key. Because diffused materials scatter light evenly in all directions, their irradiance, which by the way is just a fancy scientific term for the amount of light energy hitting that surface, looks exactly the same no matter where the player's camera is. Whether you're standing to the left of a chalk wall or to the right of it, the base lighting on that wall is completely identical. This viewpoint-independent appearance makes diffuse global illumination the absolute perfect candidate for our optimization. Which brings us to section 3. A multi-user problem. This is where we hit the core flaw in how we currently build multiplayer cloud gaming architectures. I love this analogy. It's like a shared cake. Imagine you're hosting a party with 1,000 guests. On the left, we have the traditional rendering model. All those cameras represent different players looking at the exact same scene. The server is acting like a frantic host, baking a brand new identical cake from scratch for every single person who walks in. You see those purple shaded areas? That is overlapping math. That's the server wastefully doing the exact same diffuse lighting calculations over and over again. It is incredibly inefficient. But the thesis proposes a radical shift, which you can see on the right. Instead of baking 1,000 separate cakes, the server just computes the lighting once, bakes one massive cake, puts it in a shared lookup table, and every player just grabs their slice of data. Section 4. the shared lighting solution. So, the big question now is, how on earth do we actually build and maintain this shared lighting lookup table dynamically across a massive server environment? Well, van der Sanden's thesis introduces this really clever centralized system. You take the entire 3D scene and chop it up into a grid of invisible boxes, which we call radiance cells. Then, right in the dead center of each box, you drop a data collection point called a probe. So now, instead of calculating the scene's lighting from the perspective of 1,000 individual player cameras, the server just calculates the indirect lighting for the objects inside that specific box once and saves it right to the local probe. The algorithm actually builds this out procedurally in 3 distinct passes. First up, the direct lighting pass, calculating your primary light sources like the sun or maybe a street lamp. Second, the gathering pass. This is where indirect bounced light is collected into those central probes we just mentioned, giving them a full 360-degree view of all the light coming into their specific box. And finally, the radiance cell's scattering pass. That collected indirect light is transferred outward onto the local 3D geometry of the game world. If a light source is really close, the algorithm carefully ray traces it for perfect accuracy. But if it's far away, it saves massive amounts of time by just approximating it, using the data it already gathered in the nearest probe. All right, section 5, fixing the memory wall. So sharing the lighting data absolutely solves the redundant multi-user math problem, but this thesis also tackles a huge secondary hardware bottleneck known as the memory wall. So GPUs, graphics processing units, are massively parallel processors. They absolutely thrive when they can do similar tasks on grouped data. But Monte Carlo path tracing, it's pretty much a worst-case scenario. When you have millions of light rays bouncing randomly all over a 3D scene, it causes what's called ray incoherence. The GPU has to constantly stop and fetch new data from the slow main memory. Think of it like this. Your GPU's fast L1 and L2 cache is like your physical desk, and the main memory is like a massive library all the way across town. A cache miss means you literally have to drive across town just to get a single book. But by using these radiant cells, the algorithm smartly limits how far those indirect rays can travel. This keeps the data highly localized. The GPU finds almost everything it needs right there on its desk, which drives up cache hit ratios and dramatically speeds up the whole rendering process. Finally, section 6, the future of rendering. With the rendering bottleneck solved through shared data and the memory wall bypassed by localizing those rays, what is the ultimate payoff here for cloud providers? This is the big takeaway you should leave with today. The experiments in this thesis proved there is a definitive crossover point where this new algorithm just completely blows traditional methods out of the water. In the old approach, if 1,000 players log in, the server's workload literally multiplies by 1,000. It scales linearly. But with the shift to centralized radiance caching, the server resources scale purely based on the physical size and complexity of the 3D scene itself. It calculates the lighting once, whether there's one person looking at it or 1 million people. Decoupling the user count from the processing power like this could also drastically lower the insane energy consumption of modern data centers, leading to much greener, way more sustainable cloud gaming. So, I'm going to leave you with this final thought. If cloud gaming providers actually adopt this shared rendering model, and our servers are absolutely no longer bottlenecked by the sheer number of people sharing a virtual space, how quickly will we see truly boundless, fully ray-traced, photorealistic virtual worlds emerge? The underlying math of light is definitely complex, but as we've seen today, unlocking its secrets might just be the exact key we need to build the ultimate shared digital reality.